Hello viewers, welcome to the Bachelor course of Population Studies. Today we will discuss about the topic Conceptual Models for Effective Designing and Planning of Population Research. This lecture describes the significance and the use of various conceptual or mathematical models in population analysis. Here we will discuss about how we can use such models in population research for the better understanding of the concept. Conceptual model is a descriptive model or diagram that shows the key element in the system of interest and the hypothesized relationship between them. It plays a crucial role in the research work. It generally clarifies what is known and not known about the system, as goes beyond simple cause and effect relationship to explore linkages and feedbacks in the complex systems. It acts as a key for developing research hypotheses, identifying variables under study, interpreting research results, and integrated interdisciplinary research. A model may help to explain a system and to study the effects of different components and to make predictions about the behavior. For example, a population system is a population with its effective environment. The major components of a population system are population itself, according to their age, stage, sex, and other characteristics. The organisms in the population can be subdivided into groups. Resources include food, shelters, nesting places, space, etc. Enemies includes predators, parasites, pathogens, etc. Environment includes air, water, soil, temperature, composition, includes variability of these characteristics in time and space. Now we can represent the above component of population system with the help of a model or a diagram number 1. The diagram number 1 named major components of population system. A population model is a type of mathematical model that is applied to the study of population dynamics. It provides a manageable way of understanding how numbers change over time or in relation to each other. Models allow a better understanding of how complex interactions and processes work. For example, ecological population modeling is concerned with the changes in population size and age distribution within a population as a consequence of interaction of organisms with the physical environment, with the individual of their own species, and with the organisms of other species. The world is full of interaction that range from simple to dynamic. Many, if not all, of Earth's processes affect human life. Methods in population modeling have greatly improved our understanding of ecology and natural world. Let us discuss classification of various models. Models that deal with population evaluation start from an initial population showing some defined characteristics and stimulate according to beforehand established rules the events that modify the size and structure of the population. Similarly, mathematical models are usually composed of relationships and variables. Relationships can be described by operators such as algebraic operators, functions, differential operators, etc. Variables are abstractions of system parameters of interest that can be quantified. Several classification criteria can be used for the models according to their structure. Number 1, linear versus non-linear. A mathematical model is defined as linear if all the operators in a mathematical model exhibit linearity. Otherwise, it is considered to be non-linear. Number 2, static versus dynamic. When the probabilities of occurrence of an event fluctuate in a function of time, the model is considered as dynamic model. If that is not the case, then it is considered as static model. Number 3, explicit versus implicit. If all of the input parameters of the overall model are known and the output parameters can be calculated by finite series of computations, the model is said to be explicit. On the other hand, it is characterized as implicit model. Number 4th, discrete versus continuous. A discrete model treats objects as discrete, such as the particles in a molecular model or the states in a statistical model, while a continuous model represents the objects in a continuous manner, such as height, weight of persons, etc. Number 5, deterministic versus probabilistic stochastic. A deterministic model is one in which every set of variable states is uniquely determined by parameters in the model and by sets of previous states of these variables. Therefore, a deterministic model always performs the same way for a given set of initial conditions. Conversely, in a stochastic model, usually called a statistical model, randomness is present and the variable states are not described by unique values, but rather by probability distributions. A deterministic model assumes that if each individual of a group of n persons has a probability p to experiment the event E, then this event will occur exactly Pn times, whereas a stochastic model assumes that the number of times the event E will occur may differ from one simulation to another and from the expected number Pn, but follows a random distribution with mean equal to Pn. Next is deductive versus inductive. A deductive model is a logical structure based on a theory. An inductive model arises from empirical findings and generalization from them. Next, micro versus macro. A macro model deals with a group of individuals presenting the same characteristics, while the micro model deals with each individual considered separately. Let us discuss the use of conceptual models in population research. The use of various conceptual models in population research plays a significant role. With the help of these conceptual and mathematical models, the researcher can explore his findings in a number of ways. These models act as a base and benchmark of research work. Let us discuss some of the models. Number first, exponential population growth. Exponential growth describes unregulated reproduction. It is very unusual to see this in nature. In the last 100 years, human population growth has appeared to be exponential. In the long run, however, it is not likely. Paul Ehrlich and Thomas Malthus believed that human population growth would lead to overpopulation and starvation due to scarcity of resources. They believed that human population would grow at a rate in which they exceed the ability at which humans can find food. In the future, humans would be unable to feed large populations. Next, simple discrete time exponential model. Nt plus 1 equals to lambda times Nt, where lambda is the discrete time per capita growth rate. At lambda equal to 1, we get a linear line and a discrete time per capita growth rate of 0. At lambda less than 1, we get a decrease in per capita growth rate. At lambda more than 1, we get an increase in per capita growth rate. At lambda equal to 0, we get extinction of the species. Next, continuous time version of exponential growth. Some species have continuous reproduction. dn divided by dt equal to Rn, where dn divided by dt is the rate of population growth per unit time. R is the maximum per capita growth rate and n is the population size. At R greater than 0, there is an increase in per capita growth rate. At R equal to 0, the per capita growth rate is 0. At R less than 0, there is decrease in per capita growth rate. Next, logistic population growth. Logistics comes from the French word logistique, which means to compute. Population regulation is a density dependent process, meaning that population growth rates are regulated by the density of a population. Think of the analogy of a thermostat. When the temperature is too hot, thermostat turns on the AC to decrease the temperature back to homeostasis. When the temperature is too cold, the thermostat turns on the heater to increase the temperature back to homeostasis. Likewise, with density dependence, whether the population density is high or low, population dynamics returns the population density to homeostasis. Homeostasis is the set point or carrying capacity defined as K. Next, continuous time model of logistic growth. dn divided by dt equals to Rn multiplied by 1 minus n by k, where 1 minus n by k is the density dependence, n is the number in the population, k is the set point for homeostasis and carrying capacity. In this logistic model, population growth rate is highest at half k and the population growth rate is 0 around k. The optimum harvesting rate is a close rate to half k, where population will grow the fastest. Above k, the population growth rate is negative. The logistic models also shows density dependence, meaning the per capita population growth rates decline as the population density increases. In the wild, you can't get this pattern to emerge without simplification. Negative density dependence allows for a population that overshoots the carrying capacity to decrease back to the carrying capacity, that is k. Next, discrete time logistical model. Nt plus 1 equals to Nt plus R into Nt multiplied by 1 minus Nt divided by k. This equation uses R instead of lambda because per capita growth rate is 0 when R equals to 0. As R gets very high, there are oscillations and deterministic cues. Deterministic cues is large changes in population dynamics when there is very small r. This makes it hard to make predictions at high r values because a very small r error results in a massive error in population dynamics. Population is always density dependent. Even a sphere density independent event cannot regulate populate, although it may cause it to go extinct. Not all population models are necessarily negative density dependent. The Allais effect allows for a positive correlation between population density and per capita growth rate in communities with very small populations. For example, a fish swimming on its own is more likely to be eaten than the same fish swimming among a school of fish, because the pattern of movement of this school of fish is more likely to confuse and stun the predator. Next, important theory in population research. Here we will explore the ideas of Thomas Malthus and his prediction for the growth of the human population and how he has used the models to explain and support his predictions. Early view of population growth. Over the years, there have been many opinions on how the human population will change over time. During the 70s, philosophers claimed that the human population would be maintained because the human knowledge and the moral constraint would make it possible to establish a world where resources are abundant. They believed that humans could control the earth and would make sure that all humans had all of the supplies they needed to survive. It was also a common belief of the time that if the population started to grow too rapidly, that people would immediately stop having sexual intercourse to help limit population growth. Next, Thomas Malthus theory. During the 70s, there was one man who was very interested in the future of human population and had an opinion very different than most. Thomas Malthus, an English philosopher who lived from 1766 to 1834, was the first man to publicly predict the limits of the human population and how population and well-being are connected. In 1798, Malthus wrote an essay on the principle of population, which explained his predictions and changed the view of many people. Thomas Malthus believed that the human population exhibits exponential growth, which is when the increase is proportional to the amount already present. With the exponential growth, the rate of increase becomes more rapid in proportions to the increasing total size. An example of exponential growth would be if a population increased from 2 individuals to 4, 8, 16, 32, then 64 individuals. Thomas Malthus found that the food production did not increase at an exponential rate but instead increased more slowly. As a result of these differences in population and food growth rates, Malthus predicted that the human population would eventually grow too large to be sufficiently supported by the food available. As a result of the growing population and limited food, Thomas Malthus thought that the world would begin a downward spiral. Overall, he predicted that the uncontrolled population growth would lead to a depletion of resources, increased pollution, overcrowding, and increased unemployment. He thought these problems would then lead to larger problems such as starvation, increased diseases, crime, poverty, and eventually war. Malthus predicted that these unfortunate circumstances would be how the earth would control the human population. He thought that these problems would lead to increased death rates and lower the birth rates, which would help return the human population to a manageable size where there would be enough resources to support the entire population. Let us discuss the important aspects of Thomas Malthus' theory. In areas of the world that suffer from extreme poverty, you can currently see Thomas Malthus' predictions coming true. In these areas, population have increased rapidly and without control. This has led to famine, diseases, and wars, which have all caused decreases in the population size of the region. When designing his predictions, Thomas Malthus did not foresee how much the world would change in the short period of time and how advances in technology would influence human population growth. In developed countries with high advanced technology, Thomas Malthus' predictions have not come true. In these areas, the advances in technology have made it possible to produce more food and keep people healthy, which have only helped increase the population. Malthus also did not predict that when the population started to increase, people would migrate to areas that were previously not settled, such as the Australia. Next, application of exponential and logistics model in population research. First one is Malthusian growth model. A Malthusian growth model is exponential growth model based on a constant rate. The model is named after Thomas Robert Malthus, who wrote an essay on the principle of population in 1798, one of the earliest and the most influential books on population. It is also known as simple exponential growth model. Malthusian models have the following form: Pt equals to P naught e raised to power RT, where P naught is the initial population size, R is equal to the population growth rate, sometimes called Malthusian parameter, and T is equal to time. It is widely regarded in the field of population ecology as the first principle of population dynamics, with Malthus as the founder. The exponential law is therefore also sometimes referred to as the Malthusian law. In this model, Malthus wrote that all life forms, including humans, have a propensity to exponential population growth when resources are abundant, but that actual growth is limited by available resources. A model of population growth bounded by resource limitations was developed by Pierre Francois Verhulst in 1838. Verhulst named the model a logistic function. Now let us discuss about logistic function. Let us discuss logistic function by Pierre Francois Verhulst. Logistic function was named in 1838 by Pierre Francois Verhulst, who studied it in relation to population growth. The initial stage of growth is approximately exponential. Then, as saturation begins, the growth slows, and at maturity, growth stops. The logistic function finds applications in a range of fields, including artificial neural networks, ecology, biomathematics, chemistry, demography, economics, geoscience, mathematical psychology, probability, sociology, political science, linguistics, and statistics. A logistic function or logistic curve is a common S-shaped sigmoid curve with equation fx equal to L divided by 1 plus e raised to power minus k multiply it by x minus x naught, where e is equal to the natural logarithm base, also known as Euler's number. X naught is equal to the x value of sigmoid's midpoint, L equals to the curve's maximum value, and k represents the steepness of the curve. At the end, it can be concluded that the use of conceptual framework or model enables a greater understanding of various aspects of population under investigation. The use of proper conceptual or mathematical model is a feasible strategy for researchers to effectively showcase their area of study. That's all with today's lecture. I hope this must have raised your concerns about this important concept. Have a nice time. Goodbye.